So step 2 is done. We have blocks for 5 constants, and through the use of the MATLAB function block, we can have an signal for the last remaining constant I as well. Now let's move on to step 3. That is to build up individual terms of the ODE as signals. Before I do that, I rearrange the original ordinary differential equations in to a form which should ease my task of conducting step 3. So how I do that is I rearrange the ODE so that on the left hand side I only have the highest order derivative term. Since this is a second order one, I only have theta dot dot on the left hand side. Only theta dot dot and nothing else. Everything else is moved on to the right hand side. And this is what we have. We have a sum of signals divided by I. Or we have a sum of terms divided by I. I can break these terms into I can break the numerator down into three sum of three terms. The first term would I color them in three different colors. The first one is a times theta dot, or a times the angular velocity. The second term is a multiplication of four signals, and the last term is just a single signal, which is b. So let's obtain these three terms as signals: the yellow term, blue term, and the green term. So the yellow one is a times theta dot. I'll move a upwards. Now this is the signal for theta dot, or angular velocity. And by right clicking on anywhere over here and dragging it up, I can obtain a branch of that signal. When I obtain a branch, it's kind of like drawing a wire in a circuit diagram, right? Throughout the entirety of this wire or branches, the signal would be angular velocity. Now in order to multiply A and angular velocity together, I need a multiply block. But what we have in MATLAB is something called a division block. And we can modify it to, so by default, it enables us to divide some value by another, and I have to modify it so that it is a multiplication of 2. How I do that is I specify the number of inputs as 2 multiplications. At the moment, in this particular lecture, we are only dealing with single element signals, so leaving it at element wise. And connect these two signals, and then you'll have the yellow term available as the output of this multiplication. This would be a times theta dot. So now let's take a look at this blue term. This is mgl times cos theta. So this would be theta. We are developing the block diagram in such a manner. So we need to obtain the cos value of this output signal. So I'll first bring in a cos block. Connect the signals. So the output of this would be cos theta. And what I need is a multiplication of cos theta with m, g, and l. So once again, I'll bring in a divide block and modify it so that it will facilitate the multiplication of 4 numbers. Erase what's already here by default and specify for 4 multiplication signs. Sorry. Connect the signals that you want multiply. We need them. Once again, I obtain a branch of a signal, already existing signal. GL. So the second term is obtained, or the blue term is obtained, and the last term would be B. So now we have signals for the three terms. That so step 3 is done. We have built up all these signals, so all these terms as signals. Let's move on to step 3. And sorry, step 4. So step 4 would mean we'll finally obtaining a signal for theta dot dot, and we'll do that by summing these three signals on the numerator and dividing it by the I signal which is on the denominator. So first let's bring up a sum block to sum these three terms. So by default the sum block can only facilitate addition of two signals. We'll modify it so that it will facilitate the addition of two signals and followed by a subtraction of a third. How I do is I erase what's already there on the list of signs. I need two additions and a subtraction. Right? That's what I use for such a requirement, and I apply it. So the output of this block would be the sum of what's in these two ports minus what's given to the third port. So I can change the order so that the minus sign comes in the middle. So it would just I did it so that my block diagram would be more, since I would need to subtract the signal from the other two. Right. So now we have the signal for what's on the numerator, for the whole expression on the numerator, and to obtain a signal for theta dot dot we need to divide it by I. So that's quite easy. We once again bring up a divide block. So what's available by default is what we need. We divide it by E. So the output of this block would be theta dot dot. So at this point, there are only two dangling ports, or by dangling ports I mean ports which have their signals not connected to anywhere else. We only have two dangling ports. I have colored them in red. One is the input to the angular acceleration to angular velocity integrator port, and one is the output of this division block. The output of this division block is theta dot dot. The input required to this integrated block is theta dot dot as well. So what remains is to connect these two. So that's it for the ODE, specifying the ODE. Now if I were to run configure the solver and run it, it would solve the ODE and store it within the store the results in the workspace. However, if we were to view the results, then we would have to go to the workspace, open up the vectors, and view them as matrices and so on. But we have the option of using a scope block for quick visualization